Welcome back, everyone. This is Dr. Gounstein, and here we are with the RStudio demo for lecture number 3. So in lecture number 3, we talked about a simple linear regression. Now I'm just going to show you how to perform a simple linear regression using R. Now, as you've seen before, we might need some packages. If you haven't installed them yet, here they are. I'm sure you've installed them already, so we'll keep moving on. You want to tell Stata what packages you're using in this file, so you'll use the library command if you haven't already done so. You'll just inform R that that's what you want to use, and let's go ahead and import the data. So there we go. Like I said, it's always nice to look at your data and understand how it works. I'll just use the I always like this describe command a lot because it gives us a nice spread of the descriptive statistics. So I'll just do that real quick. Okay, so one just point real quick is, again, I want to reinforce the intuition about what a regression is, and also, again, give us some ideas as to what the data looks like in the relationship. So in this quick demo, I'm just going to look at the relationship between wages and education. And I'm working my way up to doing a simple regression of wages regressed on education, which would give me some understanding of how wages and education are related. So, but first, let's just do a scatter plot. And so I'm going to use the ggplot2 library, and I'm going to produce a scatter plot of the wages variable graphed against education. So in R, the way we do that is I'll just create this plot object. I'll call it PL for plot equals ggplot. I put in the data set. The data set I need is wages, and then comma, put in the aesthetics. In this aesthetics here, I need to specify what is the x-axis and what's the y-axis. In this case, I want education on the x-axis, wage on the y-axis. And then, as you've seen before, we've seen a histogram and a kernel density function. In this case, we're doing a scatter plot. And in R, the way you indicate that is by using this plus geom underscore point. So point just means scatter plot. Okay, so we'll create that object, and then we'll go ahead and print it out. And then here we go. Here is our scatter plot. I might zoom in on it. So here, education is on the x-axis, so we can education goes from 0 to maybe about 18 or something, and then the wages. So we can see the wages here on the y-axis. Okay, and now what a regression model is doing is it's trying to fit a linear line to this data. So in this two-dimensional space, it's really easy to visualize. What we're trying to do is we're trying to find the linear line that best fits this data, that best describes it. Like if we could summarize this data with one linear line, what would that line be? That's really what we're doing when we're fitting a regression. So just real quick to kind of get an idea of what it is that I'm saying, I'm going to add to this plot. I'm just going to reproduce the same plot, but I'm going to add a linear line to it. So I do that by adding this plus geom smooth using the formula y regressed on x. You don't need to understand all the details here. I'm going to use the method LM, which stands for linear model. I'm going to suppress the standard errors. That's what those commands are. Don't worry too much about all the fine details. I'm just adding this, and what this is going to let me do is I'm going to add a linear model to this scatter plot. So here we go. This linear line here is the best fit linear line to the scatter plot, to the data here. And so this line is the best linear approximation to the data that we see, the wage, education, so the wages data set. And so this linear line captures the relationship as best we can using a linear line between wage and education. And this is basically what we are doing when we run a regression, is that we are figuring out what this line is. You'll remember from the lecture that the intercept term from a regression will show us the intercept, the point where the line intersects 0 here. And the coefficient is like a slope. It shows us the slope of the line. So when we run a regression in just a moment, we will actually get the intercept and the slope for this line that we see visualized here on the plot. So let's go ahead and do that. So here is the regression model. So in R, it's straightforward to run a regression, although there are a handful of additional notation we have to include relative to using stata. So first we'll write out the command for the model. So when we run the model creates a data object. We have to give that data object a name. I'm calling it model1, but you could call it whatever you want. I could also call it the Dr. G model of wages. I could call it anything I want, but I'm just going to call it model1. Okay? Whoops. Okay, I'm going to just call it model1, all right? And then I'm going to use the command called LM, linear model. That's what that command stands for, LM, linear model, just telling it we're going to do a linear regression. I take the dependent variable, put it in first. The dependent variable here is wage, same thing as we have on the y-axis. And then I use this little squiggly line, this tilde. That means on. In our notation, it means on, and so this means we are regressing the wage variable on or on to some other variable. In this case, that independent variable is education, so we are regressing wages on education. That's what this notation means. All right, that's our model. Here's the regression model, our simple regression model, comma. And we need to tell it what data set we're using. We are using the wages data set. That might seem obvious now because we only have one data set in our global environment. But in the future, when you're doing data analysis, you might have many data sets. And so it's important to tell Stata what data set you're using. So if we run this, we will generate the data object, model1. And now I just want to report the results. So we'll use the summary command for model1. And this shows us our regression results. So here we go. We have the intercept term. Here's the estimate of the intercept with the standard error and the p-value. And then we have the coefficient for the education variable right here, 0.545 rounding, standard error, and the corresponding p-value. Now you can see here that it uses stars to indicate significance. One important thing to notice here is that R, the summary command in R, uses their stars slightly differently than we've learned. So it's important to just take a look that a little dot means the 10% level, 1 star indicates the 5% level, 2 stars indicate the 1% level, I should say, 0.01, and then 3 stars indicate the 0.1% level. So they use the stars a little bit differently. It's important to make note of that when you're translating this into your table of results. Although in this case, it doesn't make a difference. There's 3 stars here. So, okay, so there we go. There are results for our regression. You'll find down here you have the R squared, the adjusted R squared, which we'll learn later, F statistic, etc. You'll see that this is the command that you ran. All right, now if we come over here to our table, to our plot, we can kind of see how these are related. You can see here that the fitted line is below 0. That is, the intercept is below 0. It's negative. And that's exactly what we find. And so here's the intercept. The intercept is negative 0.93. Okay. And then this line has a slope. What's the slope? Well, the slope is the coefficient on the education variable. And so the slope here is 0.545. And so what this is telling us is it's giving us the information for the line, the linear line, that best fits the data when we compare wage and education. So that's what we've done here in this regression. And then just very quickly on interpretation, how would we interpret this? Well, first we note that it's statistically significant. That means we can comfortably conclude that there is some statistical relationship between education and wage. And so when I look at this, what I would say is that wages are $0.545 higher for every additional year of schooling. Okay. Now, if the variable wasn't, or if the coefficient wasn't statistically significant, I would say there is no relationship between wages and education in the data. But in this case, there is a relationship because it's significant. And so I can say that wages are about 54 cents higher for each additional year of education on average. Okay, great. Hope you enjoyed the lecture. We'll see you next time.